Yes, Shane, am I audible and visible?
Yeah, yes, you are. Yes.
Hi, sir. How are you?
Good evening.
Good evening, sir. I'm there. Yeah.
Wait for Sanjeevani and others to join.
Okay, sir.
Hi, good evening.
Good evening, Khalid. Today we'll start with probability and we will be doing the base theorem also, right? So first, what is the probability and conditional probability? I'm waiting for a few of you to join. Hassan, Abdul, and Sanjeev. Let them join. So the first and the very important part that we do today is probability theory. So let us go and understand what is probability, how probability is a very important phenomena that plays a very, very important role, right? So basically, there are two different types of phenomena that we have. One is your deterministic, and the other one is your non-deterministic. So what are the phenomena that we are having? We are having two different phenomena. One is the deterministic, and another one is a non-deterministic phenomenon. So in a deterministic phenomena, what happens, guys? There exists a mathematical model that allows a perfect prediction of the outcome. So example that exists in physics, chemistry, and in other branches of sciences that basically the model will allow and it will help us to predict the phenomena and what's the outcome of the phenomena. But in a non-deterministic phenomena, there is no model that exists that allows perfect prediction and the phenomena's outcome. So there lies a difference between a deterministic phenomena and a not deterministic phenomena, right? So in a non-deterministic phenomena may be further divided into two different groups. So what are the groups in which non-deterministic phenomena is divided? First group is called random phenomena and the second one is called as the haphazard phenomena. So random phenomena is the one where we are unable to predict the outcome, but in the long run, the outcome exhibits statistical regularity. So that is what is called as your random phenomena. So we are unable to predict what will be the outcome. In the haphazard phenomena, what actually happens in the haphazard phenomena is that in the haphazard phenomena, you have basically the other very important role being played. Example, Abdul has joined. Yes, Abdul, welcome. Good evening.
Good evening, sir. How are you?
Yeah, fine. We just started up with probability. We were just
Sorry, I
discussing
got late.
little bit late. Not an issue. I'll just give a brief overview. In a probability, I was explaining about the mathematical model that allows us to predict the phenomena and the outcome. Okay, so we got the mathematical model that can help us to predict what is the outcome, right? So what is the outcome that we can predict? That is through a phenomena. So we have two different form of phenomena. One we have is a deterministic phenomena, which allows a perfect prediction of the outcome. And the other one that we were discussing was a non-deterministic phenomena that allows the perfect prediction, the phenomena's outcome. So there's no mathematical model for a non-deterministic phenomena, but there lies a mathematical model for a deterministic phenomena, right? Then there is a random phenomena and there is a haphazard phenomena. So what's a random? Unable to predict the outcome, but in the long range, the outcome exhibits what? It exhibits the statistical regularity. Haphazard phenomena are the unpredictable outcome. So it shows what? It shows statistical regularity in the outcome, but unable to predict the outcome is the random phenomena. So there is a random phenomena and there is a haphazard phenomena. And this is how the phenomena can be deterministic or non-deterministic. In non-deterministic, we can have a haphazard phenomena or we can have a random phenomena, right? So haphazard phenomena basically unpredictable outcome. So that in the long range, it exhibits the statistical regularity in the outcome. So such a phenomena exists with any non-deterministic phenomena that exists in the long run, which exhibits statistical regularity eventually, right? So in the random phenomena, there is a unable to predict the outcome. So what are the examples of random phenomena when we are unable to predict the outcome in the long run? For example, tossing a coin. Tossing a coin, which will have two different outcomes. It can either be head or it can be tail. But in the long run, can we predict 50% of the time head will occur or the 50% of the time tail will occur? So how do we go ahead and we predict what will be the outcome, whether it will be head or whether it will be tail, right? Rolling a dice. So when you roll a dice, we are unable to predict the outcome. What will be that outcome in the long run? Can we determine whether that each outcome will occur 1/6 of the time and what symmetry are we using each time? So one side should not occur more frequently than another. Suppose you're rolling a dice. So there may be chances that you may get one, or you may get two, or you may get three, or you may get four, five, or six. So one can determine that each count will occur 1/6 of the time. So what is the total outcome? 6 is the total outcome. That means you can have the faces of the dice as 1, 2, 3, 4, 5, or 6. So what is the total outcome is 6 and 1 is 1/6 is the probability of that particular outcome. So either you can have any one outcome out of these 6 outcome when you go ahead and you roll a dice, right? Now, very important is what are the definitions that we use in this particular case. The first is the sample space. The sample space is the one that we use for a random phenomena. What is a
Your
random?
voice is
phenomena?
not clear. It's cutting.
Yes, is it clear
frequently.
now? Yes, Abdul. So first we use the random phenomena. So what happens in the random phenomena? In the random phenomena, we'll get all the listed sample space. So basically, what is the sample space? The sample space for the random phenomena is the set of all possible outcomes. So suppose when you roll a dice or you toss a coin. So what are the outcomes that you have? You have head and tail. That is the outcome when you toss a coin. When you roll a dice, the outcome that you are having is 1, 2, 3, 4, 5, and 6. So the total outcome that you have is basically the possible outcome of an event or a phenomenon that you're having is called as a sample space. So sample space gives you what? It gives you all the possible set of outcome, right? Tossing a coin will have a sample space too. That means it will have the outcome as head and tail. Rolling a dice will have a possible outcome as 6. It can be 1, it can be 2, 3, 4, 5, and 6. So these are the sample space when you toss a coin. This is a sample space when you roll a dice, right? So what are these? These are the sample space when you are rolling a dice or when you are tossing a coin, right? Now, what is the event space? So event space is any subset of a sample space. Any subset of a sample space is called as what? Any subset of a sample space is called as an event space. So not necessarily all outcome of the random phenomena that we are getting. So any set of outcome for a particular random phenomena that we get is said to be an event space. So event space is what? It is a subset of a sample space, right? So an event is said to be occurred if the outcome has been observed. That means what outcome lies in a given event. So out of a given sample, suppose you are rolling a coin or you're spinning a coin for a toss. So what is the outcome whether you get a head or tail? So that is the event, whether you're getting a head or you're getting a tail, right? So event is said to have occurred if the outcome has been observed or where the outcome exactly lies, right? So rolling a dice, as we say, these are the basically the sample space. And what is the event space? The event space that an even number is rolled. So when you roll a dice, you're getting either 2, 4, or 6. What is the sample space? 1, 2, 3, 4, 5, 6. But out of a sample space, you got the event space. The event space is what? The event space is a subset of a sample space. So when you roll a dice, you have the outcome 1, 2, 3, 4, 5, 6. And the event that an event number is rolled is 2, 4, 6. Or an odd number is rolled 1, 3, 5. So 1, 3, 5 if the odd number is rolled. 2, 4, 6 that an even number is rolled. So this is a subset of your sample space. So event space is always a subset of your sample space. So null event that does not contain any outcome or no outcome is a null event. And the entire event, that is the sample space with all outcomes. So we can have empty event that never occurs, or we can have all the event that always occurs, that is the sample space S, right? Now, if you must have studied the set theory. So if we got a two different set A and B, will be the two different event, and the union of the event A with the union of the event B, that can be denoted like this. So we got two different event A and event B. So we got a union B where the element belongs to the event A and they also belongs to the event B. So that is called as E. which is an event which belongs to a set A, or we got the event E that belongs to set B. So A and B are two events, and then A and the union of these two events, A and B, can be defined or it can be denoted in this way, right? So this is called as the A union B event. If the event occurs, then basically we'll be having the union of two different events written like this. We can also have an intersection. An intersection can be the two event A and B, which is being defined. And the elements which are common to the event A and event B can be defined or they can be represented in this particular way, which is called as intersection, right? And this is how the intersection of the two event A and the event B that occurs can be represented. Complement. Complement means A may be any event, then the complement of that event can be defined where it belongs to A, but it does not belongs to the entire A complement. So A complement is what is there is A, but the element that does not belong to A is A complement. So that is a complement of a particular event that can be denoted or that can be defined, right? So the event A complement occurs if the event A does not occur. So if the event A does not occur, then the A complement occurs, right? So now we know that union, intersection, and complement will be helping us in recognizing the two different events, how it occurs. So when we can tell that two different events A and B are mutually exclusive, we can tell the event A and the event B are mutually exclusive if their intersection is null. So if the intersection is null, then the two events A and B are said to be, or they are called mutually exclusive. If the two events are mutually exclusive, they have no outcome in common. So there is no outcome in common. They can't occur at the same time. The outcome of the random experiment cannot belong to both the events A and B, right? Now we come down to a very important topic, that is probability, because we need to know probability, and for knowing the probability, these basic concepts that you should know, right? So what is the probability of an event taking place? So for knowing the probability of an event, we should know what is the sample space and we should know the event space. So suppose if you toss a particular coin or if you roll a dice, then we need to know what is the probability of getting even numbers when you roll a dice. What is the probability of getting odd numbers when you roll a dice? So it is the number of outcome in the event space divided by the total number of outcomes. So when you divide the number of outcome in the event space with a total number of outcome, what you get the probability of an event. So you'll be getting a probability of event when you divide the number of outcome in an event space with the total number of outcome. I'll give you an example. Suppose you roll a dice. So the total number of outcome is from 1 to 6. So your sample space will be 6. But suppose you when you roll a dice, you get even numbers 2, 4, 6. So that is 3 by 6. So 3 by 6 is 1 by 2. 1 by 2 is the probability of getting the even numbers when you roll a dice. So what is the probability of getting odd numbers when you roll a dice? That is 1, 3, 5. So 3 will be your event space. 6 will be your sample space. So 3 by 6, 1 by 2. So 1 by 2 is the probability of getting odd numbers as an outcome when you roll a dice. 1 by 2 is the probability of getting even numbers when you roll a dice. So that is how we calculate the probability based on the event space and on the sample space. Now, this is the definition of the probability, that is the number of outcome in the event space by the total number of outcome. And there are number of examples that we can quote unquote in this regard, right? Then there must be some rules for applying probability. So what are the rules that we apply for doing probability, right? The additive rule. So additive rule is mutually exclusive event. So mutually exclusive events are those events where the intersection, I mean, they don't have any particular common element for an event A and event B that is happening. They'll not have any particular common element. So that type of event is said to be what? That type of event is said to be a mutually exclusive event. So what is a mutually exclusive event? A mutually exclusive events are those events there is no common element between these two events. So that particular event is said to be a mutually exclusive event, right? If the two events are mutually exclusive, they have no outcome in common. That is, they can't occur at the same time. So this is what is the interpretation of an event that are mutually exclusive with respect to each other, right? So this is how mathematically it can be denoted, that is to event A and the event B. This is the intersection, or this is basically the union. So union of the two event A or event B can be like this when they are mutually exclusive. Next is the additive rule. So additive rule in general gives us the mathematical implementation of the two event A and event B minus the intersection of the event A and B, because the intersection is null because the events are mutually exclusive. So this is the union that we have done, the union of the event A and the union of the event B. So all the outcome from the event A and all the outcome from the event B, their union. So this is an example of Saskatoon and Moncton are the two cities, two of the cities competing for the World University Games. And the organizer are narrowing the competition to final 5 cities. So there is a chance of 20% that Saskatoon will be among the final 5. There is a chance that 35% that Moncton will be amongst the final 5. And 8% chance that both Saskatoon and Moncton will be amongst the final 5. So what is the probability that Saskatoon or Moncton will be amongst final 5? So this is basically, there are two cities which are competing for a World University game, and the organizers are narrowing the competition to the final 5 cities. Now, what is the probability or the chances of the first city among final? That is 20%. What is the chances of the second city among the final 5? 35%. What is the chances that both the cities will be among the final 5? That is basically 8%. Now, how do we find out to this probability? So let A be the event that the Saskatoon, that is the first city, is among the final 5. Let B be the event that Moncton, that is the second city, is among the final 5. So probability of the first city to be in the final 5 is 20%, which can be represented as 0.20. The probability of the second city among final 5 is 35%. That can be represented as 0.035. Probability of both the city 1, and that is A, and city B among the top 5, that is their intersection, is 8%. That is 0.08. So we calculate the probability of the first city A union the probability of the second city B minus the intersection of the probability of the first city and the second city. So 25% plus 0.35, 35%, minus 0.08, that gives us 0.47%. Will be the probability of both the cities reaching the final 5, right? So this is how we calculate this particular, and that is the complement rule. We do 1 minus the probability of event A that give us the complement. So complement that belongs to A, that does not belongs to A will be the complement of A, right? And that is how we see the complement, which the complement for a mutually exclusive event, their union can be represented in this particular. So this is how we represent the complement of two different events. So are we through with probability? Have you understood what is probability and how we calculate the probability? Before we jump into conditional probability and we see how is the conditional probability can be checked or it can be evaluated, right? So is this clear with the probability, whatever we have done right now? Yes. Any doubts
Yes,
you're
sir.
having till now? Is it okay? Okay, fine. Now what we are we're interested in doing some numericals based on what we have discussed with respect to probability. Okay. So let me go through and share a few numericals with you all so that you understand how this probability can be done. Let me stop sharing and go to some numericals. So is the numerical visible to all of you? Let me check once. Can you all see the numerical for the probability that I'm sharing right now? Is it visible?
Yes, sir.
Yes, sir.
Okay. So a coin is thrown 3 times. What is the probability that at least one head is obtained? So let me discuss the solution. So you can try with the next one. So what is this telling, guys? It's telling basically a coin is thrown how many number of times a coin is thrown 3 times. So 3 times means you will be throwing a coin 3 times. So what are the probability? So what are the possible outcome that you can have? So in this case, the sample space will be head, 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 tail, head, tail, head, tail, head, head, tail, tail, head, tail, head, tail, head, tail, tail, and tail, tail, tail. So how many the outcome that you have in a sample space? So you have total 8 outcomes. That is when you throw a coin 3 times. When you throw a coin 3 times, the outcome that you have is 2 into 2 into 2. That is 8. But what is the event here? The event space here, which is a subset of a sample space, that you should at least have one head. So how we can have one head? So you can count the sample space. There are 7 such outcomes where we have at least one head. So the probability that is the event space by the sample space, if we calculate here, is 7 by 8. So 7 is basically your event space and 8 is your sample space. So you get the probability here as what? You get the probability here as 7 by 8. Is it clear how we are getting 7 by 8? Are we all on same page?
Sir,
Yes,
can
sir.
you repeat, please? It's not clear to me.
Again, I repeat, there are 3 coins, and what we are doing is that we are throwing the 3 coins at the same time. So basically, one by one, a coin is thrown 3 times. You take a coin and you throw it once, twice, and thrice. So the outcome, what outcome that you can get? You can get a sample space, head, 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 or you can get a outcome, head, head, tail, or you can get a outcome, head, tail, head, or you can get a outcome, tail, head, head, or you can get an outcome, tail, tail, head. Or you can get the outcome tail, head, tail, head, tail, tail, and tail, tail, tail. Now, out of these 8 outcomes, there are 7 such outcomes where you have at least one head. Out of these 8 outcomes, there are 7 such outcomes when you throw a coin 3 times where you have at least one head. So the probability of getting at least one head out of this total outcome is 7 by 8. So what is the probability that you get at least one head? That is 1 minus, that is 7 by 8, or you can write it like this, 1 minus 1 by 8, which is also equal to 7 by 8. So this is how we calculate the probability when we toss a particular coin 3 times with the total sample space is 8 and the event space is 7. What is the event? The event of getting at least one head when you throw a coin 3 times. Is this clear? Are we all on same page?
Yes, sir.
Yes, sir. It's clear now. Thank you.
Now the second one. Find the probability of getting a number card when the card is drawn from a pack of 52 cards. What is the probability of getting a sample, a numbered card when a card is drawn from a pack of 52 cards? What are the number cards? Number cards are 2, 3, 4, 5, 6, 7, 8, 9, 10. And what is JQKA? JQK is basically the face card and A is a honors card, right? So if you have a card, total pack of 52 cards, the probability of getting a numbered card that is from 2 to 10, that is 9. Why we are multiplying 4 into 9? Because there are 4 different types of colors. We got diamond, we got spread, we got clubs, and we got hearts. So we got 4 different colors. So 4 different colors and the number card is 9. So 4 into 9 is 36. So out of 52, 36 divided by 52, which gives us the probability of 9 by 30. Are you getting it? Is it clear? Why we are getting 9 by 32? So what is
Yes,
the sample space here? 52 cards. What is the event space here? 36. Why 36? Because there are 4 colors. For each color, 9 numbered card. 9 into 4 is 36. So we divide 36 by 52. So what we get? We get the probability 9 by 30. Are we all clear on this this particular probability that we are discussing now?
yes, sir. Got it.
Are we all on the same page? Shall we go to the next one? Yes, I'm going to the next one. There are 5 green balls and 7 red balls. 2 balls are selected one by one without replacement. There are 5 green and 7 red balls. 2 balls are selected one by one without replacement. So find the probability that the first ball is green and the second ball is red. So total balls are 7 plus 5 is 12. Total number of balls that is in the basket from where we are selecting one by one. Total balls are 12. 7 plus 5, that is 12. Out of 12, we are selecting the first ball. The first ball, what is the probability that the first ball is green? So how many green balls? 5. So 5 by 12. Now, since we have selected one green ball, so number of balls that are remaining is 11. The number of balls that is remaining is 11. From 11, how many red balls? 7 red balls. So 7 by 11 is the probability for selecting the red ball. 5 by 12 is the probability of selecting a green ball. So the total probability of selecting green and red ball is 35 by 130. 12 11s are 130. 5 7s are 35. So what we get? We get the probability as 35 by 132. That is basically the total probability of selecting a red ball and a green ball when you have total 12 balls, one by one, where we find the probability that the first ball is green and the second ball is red. Okay. This is the another one. When two dice are thrown, what is the probability that their sum is 7? What is the probability that their sum is 7? Means the sum of the outcome in the first dice and the second. What is the event space here? What is the sample space here? 36. Why? There are 6 outcomes from the first dice, 1 to 6. There are 6 outcomes from the second dice, that is 1 to 6. So 6 into 6, there are 36 ways we can get the outcome when we are throwing the 2 different dice. Then what is the favorable cases? What is the event space here? The event space that their sum is 7. 1, 6 is 7. 2, 5 is 7. 5, 2 is 7. 3, 4 is 7. 4, 3 is 7. So there are 6 ways where we can get the sum of the numbers or the outcome in the first dice and the second dice is equal to 7. If you add 10, you get it 7. So that becomes how much? That becomes 6 by 36. That is 1 by 6. So 1 by 6 gives you what? It gives you the probability of getting a sum 7 when 2 dices are thrown together. Is it clear? How do we get the probability in this particular case? Yes, everyone?
Yes, sir.
Yes, sir.
Okay. Then we go ahead with the next one. Suppose one card is drawn at a random from a pack of 52 cards. So there is a 52 card and one card is drawn in random from a card of 52. So find the probability that it is a honors card. Find the probability that it is a face card. What are honors card? A, J, K, Q, K are honors card. And how many honors card you have? Because there are 4 colors: clubs, diamonds, hearts, and spread. So basically 4 into 4. You will have 16 honors card for different color from a pack of 52 cards. So 16 by 52 will give you a probability of an honors card is 4 by 30. What are face card? The face card is JQK. So there are 3 face card. So what is the probability of getting 3 face card of different color from a pack of 52 cards? So 3 into 4 because there are 4 colors. So we'll have 12 face card and 12 by 52 gives us a probability of 3 by 30. So this is what we get a probability of a random card picked up from a pack of 52 cards. Another one, we'll do this one. Now, you need to know how permutation and combinations calculate, right? I'll show you how do we do the permutation and combination first. Now, 2 cards are drawn from a pack of 52 cards. So find the probability that both are diamond or both are king. So from a pack of 52 cards, how many cards are drawn? 2. So 52 combination 2. That is the total number of ways we can draw 2 cards from a pack of 52 cards. Now out of these 2 cards, both the cards will be diamond. So how many cards are diamond in a pack of 52 cards? There are 13 cards that are diamond. So 13 combination 2. How many cards are king? There are 4 kings out of 52 cards. So basically out of these 2 cards that we have picked up from a pack of 52, there can be at least 4 kings. So what is the combination? 4C2. So if you add 13C2 plus 4C2 divided by 52C2, you get the probability. Now, how do you do permutation and combination? Because when you calculate probability for these type of sums, now you need to know permutation and combination. So how and in what way we go ahead with permutation and combination when we are supposed to calculate the probability of two different events like this, right? So I'll go down with permutation and combination. So if it is 13C2, so this is the formula by which we can calculate the permutation and combination. So from a pack of 13 cards, if you are from a 13 diamond, if you are selecting two cards, so the plugging in our number is n is equal to 13 and r is equal to 2. So 13C2 will be 13 factorial divided by 2 factorial multiplied by 13 minus 2. So 13 factorial, 2 factorial into 11 factorial will give us a combination of choosing a particular card or that particular number like this. And how do we calculate the factorial? Suppose if we have 13 factorial, that means 13 into 12 into 11 into 10 into 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1. 2 factorial is 2 into 1. 9 factorial is 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1. So this is how we calculate the 13C2, 52C2, and this is how the permutation combination is what in the problem. So this is the formula. You can all write down the formula. I'll share the screenshot in the chat box. So when I'm giving you the sums on probability, we'll use this formula to calculate the probability of a particular event taking place or the event space that we have taken into consideration. And how do we use this event space in calculating the total outcome based on the given set of the outcome that we are getting, right? So here, what is the numerical that we were discussing? That is this one. It using the concept of your permutation and combination. And how do we go with permutation and combination? So that we find the probability that both are diamond or both the cards that you have picked up from a pack of 52 cards are king. So can you try this one? I'll give the sum. 3 dice are rolled. I'll put it in the chat box. I'll not share the solution. You try to solve this one and you tell me what is the answer. So the question is on the chat box. You guys solve it and then I'll show you the solution, right? Go ahead with this one. What is the question? Instead of rolling a 2 dice, how many dice we are rolling? 3 dice. So what is the probability of getting at least 1 4? Can you do this one? Can you try this one? Yes, Aparna?
Yeah, doing, sir. At least one form is more than four, right, sir?
Yes. So in this case, your sample space will be what and your event space will be what? Any idea?
Sir, samples will be 6 into 6 into 6.
Because there are three
2 and
dice, so you
6.
have 6 into 6 into 6. That will be your sample space, right?
Yeah. So the combination, it will be combination, no, sir. 3,
Yes.
3C, 6, I think so. It is 4. So it will be 3C 216 or how it will be just?
Okay, it will be total sample space that we are having here, Aparna. It will be 6 into 6 into 6. And the probability of getting number for at least one time, that is 5 by 6. Because if for the first dice, there are 5
Yeah.
such events. So it will be 5 by 6 into 5 by 6 into 5 by 6. So 1 minus, because getting a number 4. So number 4 is a one outcome. So it's a event space, that means it is 5 by 6. 5. So 5 for the first dice, 5 for the second dice, 5 for the third dice. And then 5 by 6 into 5 by 6 into 5 by 6. That gives 91 by 216.
Yeah.
Got it? Can you try this one? I'm giving
Yes, sir.
8-1. Here, a problem is given. And you need to go ahead and solve that problem. And the probability is provided. So what is the probability the problem is solved? So what you have to identify? You have to identify the probability that the problem is solved. It's given to the three different persons. The three different persons are trying to solve the problem, and the chances for solving the problem is 2 by 7, 4 by 7, and 4 by 9. So what you have to find out? You have to find out what is the probability that the problem is actually solved. So what is the sample space that you are getting here, and what is the event space that you are getting here?
Sir, 32 by 441.
35. Let me check. So here, the probability of solving the problem is by the first person is 2 by 7. So 1 minus 2 by 7. The probability of solving the problem by the second person is 4 by 7. So 1 minus 4 by 7. The probability of solving the problem by the third person is 4 by 9. So 1 minus 4 by 9. And then you get the probability for the solving the problem by the first person, second person, and third person. Like this, 1 minus 5 by 7 into 3 by 7 into 5 by 7, which gives you 122 by 147. That gives you the probability of solving the problem by the first person, by the second person, and by the third person. You get the total probability, how the problem is solved by all the three different persons, right? The first person, the probability is 2 by 7. So 1 minus 2 by 7. Second person, the probability is 4 by 7. Third person is 4 by 9. So you find the probability of solving the problem by the first person, second person, and the third person. Now, can you do the ninth one? Find the probability. What is the problem? So how we can go about it, right? So I'm putting the numerical in the chat box. So you have to find out what is the problem. So we are not tossing one or two, we are tossing 5 coins. And what is the probability that we are getting 2 heads when 5 coins are tossed together? It's very simple. We get the probability when we toss 5 coins. So we'll be getting 5C2. We use the formula and we'll get 2 to the power 5 is 32. That is 10 by 30. That is 5 by 60. Have you understood the probability? Abdul, Aparna.
Yes, sir. Yes.
With the conditional probability, because once you are through with the probability, next you should know what is. Then we go into the Bayes theorem. So it should be a systematic approach towards the Bayes theorem. Before we go to the Bayes theorem, we should know what is the conditional probability and how we go about the conditional probability and in what way the conditional probability is different from the standard probability that we are using. So let me share that conditional probability. What is based on probability. But what we like to explore is that we like to explore conditional probability. So conditional probability before observing the outcome of a random experiment how this information can be used in the prediction of the outcome, which is very much important. How should the probability be adjusted? And what type of information that we need to keep in account. So basically, the information that we have used in the prediction and what come of outcome, which is associated with the information playing a very important role in the conditional probability. Should the probability be adjusted? What are the things that we need to take into account when we go ahead with the conditional probability? So information is given in the particular format and how we go ahead with the conditional probability. So suppose that we are interested in computing the probability of an event A and we have been told that the event B has occurred. Then the conditional probability of event A given event B is defined can be like this. And what is the conditional probability of an event A when the event B has already occurred?
SP intersection B divided by. Similarly,
Is intersection event, that is A and B, divided by the probability of the event B, where the probability of event B should not be equal to 0. So how do we define a conditional probability? We define a conditional probability by using this formula. What is the formula that we're interested in computing? The probability of a particular event when we have been told that the event B has already occurred. Then the conditional probability of an event A, even event B is defined, can be represented in this particular format, right? So this is how we can represent the conditional probability of two different events taking place. Now, when we work on with the conditional probability, so these are the rationals that we are being told. The event B has occurred, then the sample space is restricted to the event B. So since the event B has already occurred, so what is the sample space? It is restricted to the event B. The probability within the event B has to be normalized. That is achieved by dividing it with the probability of an event B. The event A can only occur if the outcome is in intersection of event A and B. So this is very important. When you do a conditional probability, because conditional probability is something different from your normal probability that you do. So if you are told that you have an event B that has occurred and the sample space is restricted to the event, then the probability within the event B has to be normalized. That is by dividing the probability of the event B. So the event A can only occur if the outcome is in the intersection of the event A and B. Hence, the new probability of event A when the event B has already occurred can be as per this rationale, where A and B intersection and the probability of the event. So this is what we take it. So this is a one example of a conditional probability. The Academy Award is soon to be shown. For a specific married couple, the probability that the husband watches the show is 80%. The probability that his wife watches the show is 65%. So this is an Academy Award where we have a specific couple, and that shows the probability that the husband watches the show 80%, wife watches the show 60%. The probability that they both watch the show is 60%. So if the husband is watching the show, what is the probability that his wife is also watching the same show? How we can go ahead or we can calculate. So this is a typical example of your conditional probability, right? So the Academy Award is soon to be shown. So let B be the event that husband watches the show. So what is the probability the husband is watching the show? 80%, that is 0.80. Let A be the event that his wife watches the show. What is the probability? 65%, that is 0.65. What is the percentage that both watches the show? 60%. So the probability of A intersection of probability of B, the event B is 60%. And the probability of event B basically is 80%. So conditional probability of a particular event A, that is the wife watches the show, depends on when the event B has already occurred. That means we know that what is the probability that the husband is watching the show. So that is coming as 0.75. Is it clear? A typical example on conditional probability. Are we all on same page?
Yes, sir.
So this is a typical example how a conditional probability is being shown based on this specific event A. So event B. So the event A taking place when the event B is already occurred and the probability of the event B is 80% and the joint intersection of the event A and event B is 60%. So the conditional probability is calculated like this, right? So this is how we call a conditional probability for a particular event. But what happens if the events are independent? Means like this. So there are different cases that we will see. But before we go into that, we come to a very, very important topic, that is a Bayes theorem, because conditional probability and your Bayes theorem that go side by side. So I'll go ahead and I'll share the Bayes theorem, and we'll have some numericals also based on the Bayes theorem, right? So let me share the Bayes theorem. So Bayes theorem will be based on the Bayes rule, and it is also based on your idea how your conditional probability is used in your Bayes theorem. So can everyone see the Bayes theorem that I'm sharing?
Yes, sir.
So we know what is a probability. A probability is a measure or the likelihood that an event will occur. A probability is quantified as any number between 0 to 1. So 0 indicates the impossibility and 1 indicates the certainty of that event taking place. We've seen an example of a probability when a coin is tossed and we get hit or we get a particular tail as an outcome, right? That we have seen. Conditional probability, basically it measures the event by assumption, pre-assumption, assertion, or evidences. So we try to find out the conditional probability. Right now, I've given you an example of a conditional probability. It is a probability of an event A when the event B is already occurred. So the probability of event A given the B, or the probability of A under the condition that B is already occurred, can be written P of AB. So that is how we calculate the conditional probability of a particular event. When to apply Bayes theorem? So we apply the Bayes theorem when you consider the theorem in this particular form, and it helps us to compute the conditional probability of a particular event based on the two set of the probability as discussed. So basically, this is how we go ahead and we apply the Bayes theorem. So what is a Bayes theorem? So Bayes was a theorem was developed by Thomas Bayes, and it shows a rational relational between one conditional probability and its inverse. So what does the Bayes theorem shows? It shows the relation between one conditional probability and its inverse. And what it provides a mathematical rule for revising an estimate or a forecast in a light of observation. So how do we revise an estimate or a forecast in light of mathematical experience and observation that is being explained by the Bayes theorem, right? So it's being designed by Thomas Bayes in 18th century. and Laplace then define the Bayes work and give it a name as a Bayes theorem. So what is the definition of a Bayes theorem? As per the Thomas Bayes, the probability theory and statistics or a Bayes law describes the probability of an event based on a condition that it may be related to the other event. So there are two different events. So what is the probability of a one event when the other event has already occurred? That is basically a part of conditional probability that we can use in the Bayes theorem to find out the actual probability. So basically the theory and the statistics describes the probability of an event based on certain condition that may be related to that event, right? So the Bayes theorem is a method of revising a probability given that additional information certain information that is related to this event, then we can go ahead and we can calculate the conditional probability, right? So A and B are two events. So P of A and P of B are the probability of the event A, and B is the probability of event B without regard to each other. Now we write P of AB, that is the conditional probability of observing a event A given that event B is already occurred or it is true. B of BA is the probability of observing an event B given that event A is already true. So here we use these terminologies or these symbols and notations in the Bayes theorem to identify the conditional probability by observing an event A given that the event B is true. The probability of observing an event B given that the event A is true. So that is how we calculate the conditional probability of two different event A and event B using the Bayes theorem, right? Now, what is the Bayesian inferences? So Bayesian inferences is a method of statistical inference that we use where we try to find out the prior probability and posterior probability. So what we are trying to find out here, we are trying to find out the prior probability or we are trying to find out the posterior probability. So prior probability, that is the initial probability based on the present level of information. So what is the present level of information? The prior probability is the initial probability. Posterior probability is based on the additional information. What is the probability of an event based on some additional information that is called as the posterior probability, right? So a sample space here is defined by what? It's defined by two mutually exclusive events. It rains or it does not rain. Third event occurs when the weatherman predicts it rains. Notation for these events can appear as below. Suppose we take a three event, A1, event A2, and the event B. So the event A1 is it rains on Mary's wedding. Event A2, it does not rains on the Mary's wedding. Event B is the weathermen predict it rains, right? So suppose we are trying to find out the condition, you apply the Bayes theorem on the three different events. Suppose Mary's wedding is going to take place in a desert where there is a probability of getting a rain, okay? Or there is a probability of not having a rain on those days when the wedding is going to take place. So in terms of probability, we know there are 5 days in a 1 year in that particular desert. In those days that it rains. So what is the A1? It rains. So there's only 5 days in a year. It rains in that desert where Mary's wedding is going to take place. So that is 5 out of 365 is the probability that it will rain only on this particular 5 days out of 365 days when the Mary's wedding is taking place. That is the probability of the event A1. Then what is the probability of the event A2? It does not rain. because it is a desert where Mary's wedding is taking place. So out of 365 days, there are 360 days where it does not rain at all. So the probability that it does not rain on the Mary's wedding is 360 by 365. So the probability of the first event it rains on the Mary's wedding is 0.01. The probability it does not rain on the Mary's wedding is 0.98. Now the conditional probability. What P of A1? So what is the probability that it rains? And the weatherman predicts it rains 90% of the time. So what is the probability of an event A1 when it rains? So it rains, the weatherman predicts it will rain 90% of the time. So that is 0.91. What is the probability it does not rain? Does not rain means it does not rain means the event A2. And the weatherman predicts it rains 10% of the time. So in the weatherman has predicted 90% of the time it does not rain. Weatherman has predicted 10% of the time it rains. Since the wedding is taking place in a desert, so the weatherman has predicted it will rain, it will not rain. When it rains, the weatherman predicts 90% of the time. So P of A1 means when the event A has occurred, what is the probability of the event B that the weatherman predicted it will rain? When the weatherman predicted does not rain, that is 10%, that is B of A. Now we put this value into this formula. That the probability it will rain on the Mary's wedding, given a forecast for the rain by the weatherman, the answer can be determined by the application of the Bayes theorem. What does the Bayes theorem suggest? P of A1 into P of B of A1 divided by P of A1 into P of B of A1 plus P of A2 into P of B of A2. So we'll just substitute these values so that we get the probability of Mary's wedding depending on the weatherman forecast, it rains or it does not rain, is 0.111. Have you understood the Bayes theorem?
Yes, sir.
Yes, sir. Very, very important that you understand conditional probability and you understand how this conditional probability is applied in the Bayes theorem. So when you do a Bayes theorem, when you do the conditional probability, you should know what is the probability of a particular event when the other event has already occurred, or you are given a probability of that particular event, right? So that is how your conditional probability plays a very, very important role in identifying and in understanding this particular probability and how this probability that we are going to calculate based on the Bayes theorem. So this is very important that we know the conditional probability, we know the formula for the Bayes theorem, and basically we have to also know how it is applied, right? So this is how your Bayes theorem and your conditional probability playing a very, very important role, right? So this is how your Bayes theorem and your conditional probability that plays a very, very important role in understanding how it is going to apply and in what scenario, what output you are going to get. Yes, Abdul, are you through with this? Any doubts, Abdul?
No, sir, so far no doubt.
No doubt. Very good. What we did with the conditional probability. Conditional probability based on some standard phenomena that we are trying to calculate. So if I give you a sum on conditional probability now, can you try to implement that? So let me share that particular thing with you. Right here, I'm sharing the screen. So you do this conditional probability and you see this one. So is it visible, Abdul? Can you see? So here we have done the Bayes theorem and we have done the application of the Bayes theorem. The So this is one of the examples where you can put it in your conditional probability. 75% of your friends like chocolates, 35% like chocolates, and also like strawberry. What is the percentage who likes chocolate? So strawberry. How will you solve it, Abdul? What the cards are selected without replacement from a standard deck. So find the probability selecting and then select. So we'll use the conditional probability. So you got a two different event and you got the probability of the event A and event B. So and you also given the intersection of the probability of the event A and event B, through which you can easily calculate the conditional probability. Is using your conditional probability. And it means the formula could be expressed in this particular way. So when we determine the probability of a particular event, when the other event is true, or then we calculate what? We calculate the Bayes theorem. And your Bayes theorem can be explained or it can be expressed using conditional probability, which is very useful when you reverse the conditional probability. It can be easily calculated and we can also calculate the joint probability, right? Like this. And this is how your Bayes theorem can be written and it helps you to calculate the Bayes rule or the probabilistic inferences that you wish to generate from your event A, event B, and the event C. So the Bayes theorem gives you what? The likelihood of a particular event being true given the A is true. P is the probability of an event A being true. PB is the marginalization, that the probability of event B being. And P of AB is the posterior probability, that is the probability of event B being true given event A has already occurred or it is true. So you have the posterior probability, you have the likelihood of a particular probability, you have a prior probability, and you have the marginalization. All the things, all the components are there in your Bayes theorem. What you have the posterior probability of a given event being true. You have a likelihood of a probability for a particular event being true. You have a prior probability of a given event being true. You have a marginalization of a probability for a particular event being true. So you have all these rules that you apply to the Bayes theorem, right? And then we use the Bayes rule. So Bayes rule is a cause and effect. So cause, effect, cause, effect. So this is will give us the marginal probability, then it gives likelihood of the probability, the prior probability, and the marginalization of the probability. All the components added in your Bayes theorem, and it looks like this, right? So here we use the posterior probability, we use the prior probability, we use the marginal probability, where all the events are in a mutually exclusive and exhaustive. All the events are what? They are mutually exclusive and exhaustive. So Bayes theorem, here we have a tree diagram that shows the probability 70 is to 30 economic growth and economic slowdown, 80 is to 20 when the stock prices go up or the stock prices goes down, right? So suppose G is the economic growth, S is the economic slowdown, U is the upward stock, D is the stock downwards. So what is the probability of economic growth of 70%? So probability of stock improves or it goes up given economy is going 80%. So what's the probability of stock going up with the condition on economy is growing up? So the economy is growing up. So what is the conditional probability of a stock going up with the condition on economy is also going up? So we form a probability form tree. So how does it looks like? It looks like the economics grows up and the stock grows up. It gives you an intersection. And then we apply the Bayes theorem. So what is the Bayes theorem? We have applied what is the probability that economics will be growing given the stock is going up or the stock went up. So what is the probability that economic grows given that the stock is going up? So this is a Bayes theorem that we apply where we have the conditional probability of 70% by giving the addition of new information that the stock went up. The unconditional probability can be 86%. So 70% is P of C. 86% is when the stock goes up, when the economy is performing better. So that is basically, these are the two conditions that will apply to the Bayes theorem. And this is how we go ahead and we calculate. This is another example where we apply the Bayes theorem. So what is the probability that the patient has a disease, meningitis with a stiff neck? A doctor is aware that the disease meningitis causes the patient to have a stiff neck and it occurs 80% of the time. So he is also aware of some more facts which are given as below. The known probability that the patient has meningitis disease is 1 out of 30%. That is the probability of patient having this particular disease. The known probability that the patient has a stiff neck is 2%. So the proposition that the patient has a stiff neck and the proposition that the patient has meningitis both can be calculated using the here we want to use conditional when the patient has a meningitis. So the doctor knows that it is 80%, right? So he's aware that meningitis causes a patient to have a stiff neck 80% time it occurs. So that is 0.8. How many patients will have meningitis? 1 out of 30,000. And what is the probability the patient has stiff neck? 0.8 into 1 by 30,000 into 0.0. So that gives us that one outpatient out of 750 patient has a meningitis disease with a stiff neck. How we can find out? By putting it into the formula, because these are the facts and figures which are provided. So once we put it in the formula, we can assume or we can find out the patient who has meningitis disease with a stiff neck, right? This is another one. From a standard deck of playing card, a single card is drawn. So the probability that the card is a king is 4 by 52. Then calculate the posterior probability when the it is a face card and it is a king, which means the face card is a king card that is drawn. So whatever the face card that is drawn is a king card. So we can find out the probability of a face card being a king card when it is drawn. And what we can get with the probability the card is a king, that is 4 by 52. The probability that the card is a face card, that is 3 by 13. And the probability of a face card when it is assumed it is king is 1. So once we put it into the formula, we get what? We get the probability that the face card is a king card. And this is another example where a financial analyst at an investment bank does a particular research, and he finds out that 35% of the company did not increase their share prices by more than 5%. In the same period, that is replace their CEOs. So we know that the probability that the stock prices go up by 5%, and we find the probability. The probability that the stock prices increases by 5%. The P of B, the probability that the CEO is replaced. P of AB, the probability of stock price increases by 5% given the CEO has replaced. Probability that the CEO's replacement given that the stock prices has increased by 5%. And when you apply the Bayes theorem, you get this probability that the share prices of a company that replaces the CEO by 5% is 6.67%. Have you understood these numericals on probability, Abdul? Are you facing any challenge, Abdul?
Yes, sir. So far good, but need more practice to go through it, so it will be more clear.
More practice. See, what we do in the probability Bayes theorem is that we take these things into consideration. Prior probability, likelihood of a probability, posterior probability, and the marginalization. So what are the things that we take into consideration when we apply the Bayes rule or when we apply the Bayes theorem? We take the likelihood of the probability, the posterior probability, the marginalization of the probability, right? And we use the cause effect. So cause effect means we take the one event and what will be the consequences when the other event is holds true. And then we calculate these things. So S is the economic growth, is the event one. Economic slowdown, that's the event two. Stock going up, stock going down, depending on the economic growth. So probability of economic growth when 70% and above, then the stock prices goes up. Otherwise, it goes down. Now we calculate the probability of economic growth and stock is going up. Probability that the economic growth when the stock went up, we can get it through applying the Bayes theorem. So how we can apply the Bayes theorem? We can use the 70% unconditional probability, 86%, the information that the stock went up, and we use the conditional probability that is called as the Bayes theorem, and then we apply the Bayes theorem. This is the case one. This is the case. Challenge, Abdul? Let me know. Is the Bayes theorem clear? Okay, very good. So you're through with the Bayes theorem and you understood the Bayes theorem. Very nice, right? Now, what we are going to do is that we will see this confusion matrix, or we'll see the false positive, true negative, and false positive. How do we apply this the true positive or true negative or false positive or false negative? So suppose gold standards that are present, so that test positives. So true positive means when you detected something as a true and it comes out to be true, that is true positive. Suppose you detected the patient tumor is cancerous and it turned out to be cancerous, then it is true positive. Suppose you detected the patient tumor is cancerous, is not cancerous, and it has comes out to be non-cancerous, then false positive. False negative, you detected the patient tumor is cancerous, but it turned out not to be a cancerous. True negatives, you tell a particular patient tumor is non-cancerous and it turns out to be non-cancerous. So these are the test positive, test negative. Gold standard, whether the disease is present or the disease is absent. So when you add A plus B, you test the positive. So whether
the tumor which was cancerous has been diagnosed as a cancerous or not. And test negative when the tumor has been called non-cancerous and whether it has come out to be non-cancerous. That is total negative. So we try to calculate the total negative and the total positive by using this contingency table: true positive, true negative, false positive, and false negative. Now, there are two very important things that we need to know. You got know about the sensitivity and the specificity. So what is a sensitivity and what is a specificity, and how do we go ahead and we calculate the sensitivity and the specificity? So sensitivity is the ability of a test to correctly classify an individual as disease. So you test positive and the disease is present, then it is called as true positive. So what is called as true positive? You test a positive and the disease is present, that is called as true positive. What is false positive? You test positive and the disease is absent, that is called as false positive. You test negative when the disease is not present, but actually this is the disease is present, so that is false negative. You test negative, the disease is not present, and the disease is found to be absent, that is true negative. So the specificity is B plus D, that is false positive plus true negative, and sensitivity is A plus C, that is true positive plus false negative. So we calculate the sensitivity, that is A divided by A plus C, that is true positive by true negative positive plus false positive, and we calculate specificity, that is D divide, that is true negative divided by false positive plus true negative. Have you understood how we calculate specificity and sensitivity, Abdul? Is it clear how we calculate specificity and sensitivity? Any doubts here, Abdul?
It's clear, sir, but it's a bit confusing. Like so many things are there, positive, negative. So it's to revise again.
Okay, I'll give you an example. Okay, suppose there was a disease, meningitis, or take a tumor. Uh, a patient is going for a tumor and he's going to scan that tumor whether it is cancerous or not. So what is the probability that this disease is confirmed in a patient and the disease is actually present? What happens? We come with a diagnosis that the tumor is cancerous, but the tumor is not cancerous. I'll take another example. Suppose a patient is predicted that he's got a COVID positive, but when the RT-PCR report has come, it shows that he's not a COVID positive. Suppose a patient is tested as COVID negative, but when the RT-PCR report has come, he is tested as COVID positive. So there can be cases like that where a patient is diagnosed COVID negative, but he's come out to be COVID positive. There are cases like that when the patient is diagnosed as COVID negative, but when the report has come, it come as COVID positive. There are cases like that when the patient is diagnosed as COVID positive, and when the report has come, it was actually COVID positive. There are cases like that when the patient is diagnosed as COVID negative, but when the report has come, he is diagnosed as COVID negative. So there are instances, there are cases when the diagnosis is carried out, the patient is diagnosed correctly or he is diagnosed incorrectly. So how we can find out the accuracy of the report, whether the patient is properly diagnosed as COVID positive or COVID negative? We can use this sensitivity and specificity. So the probability of a test being positive and the disease is present, the probability of a test being negative and the disease is absent. So what is the probability that a test is positive and the disease is present. What is the probability of a test being negative and the disease is absent? So how do we find out? How do we go ahead and how do we find out the specificity and we find out the sensitivity, whether the probability of being tested positive when the disease is present, the probability of being tested negatively when the disease is absent? How we go ahead, how we find out the specificity and the sensitivity of these particular. Very important that we find out the specificity and the sensitivity of these disease that is being tested, right? So it's very, very important that we go ahead and we find out the sensitivity, or we go ahead and we find out the specificity of a particular event or the disease being tested positively, or a disease being tested and negatively and it has come out to be negative. So disease present or disease absent. So how do we find out the disease is present or the disease is absent? We can find out whether the disease is present or whether the disease is absent based on the uh, sensitivity and the specificity. So that is true positive, false negative, true negative. So these are the 4 parameters which will help us to find out whether disease is present or it is absent. So it is the ability to correctly classify an individual disease free is called the specificity. That is true negative divided by the true negative plus false positive will give you the specificity. That is the probability of being test negative when the disease is absent. So that is basically the specificity. So probability of being tested negative when the disease is absent. Now, 100% with a primary angle closure glaucoma. Glaucoma is a disease of eye, which is the eye problem, and ophthalmologists look into that particular. Are examined by Van Hangrit tests. 75 of them had narrow peripheral anterior chamber depth, and the sensitivity of the peripheral anterior chamber depth examination to the glaucoma is specified. So PAGC is as a gold standard for detecting whether a person has a glaucoma eye disease or not. So what is the standard, gold standard? 75% means 75% is true positive, means the disease, and 15% is true negative. 25% is false positive, false negative, and 85% is false positive. So this is basically the gold standard. Now we calculate the sensitivity and specificity. So sensitivity is 75 divided by 100. That is means 75 plus 25, which gives 75%. And specificity is 85, where you have 85 plus 1500, that gives you 85%. So this is how we find out the specificity and the sensitivity for a person being diagnosed with a disease glaucoma, depending on the gold standard. So this is how. Have you understood the numerical, Abdul? Is it clear? Have you understood?
Yes, sir. It's clear. It's clear, sir.
Sensitivity? How do we find out the specificity of a particular person suffering from a glaucoma, and what are the gold standards that we use to find out whether the person is suffering from glaucoma or not, and what are the gold standards so this is how we calculate the sensitivity. What are the gold standards that we use for specificity and for sensitivity, right? And what is the probability of a patient being diagnosed with these particular outcome, right? So it's very, very important that you know. I'll just put this example here so that you all understand how to calculate sensitivity, how to calculate specificity, what are the gold standards that we need to use to calculate the sensitivity and the specificity of a particular disease that we are taking into consideration. Okay, understood? Is it clear? What are the gold standards that we are using? What are the sensitivity? What is the specificity? And how is the sensitivity and specificity playing such an important role when we are trying to calculate all these different scenarios, right? So what we did with probability, we did with conditional probability, we did with Bayes theorem, we did with the application of the Bayes theorem, with the sensitivity and specificity. How, what is the probability of sensitivity and specificity when we are dealing with these particular numericals? So is it clear, Abdul? Any doubts you have, any queries you have, any challenge you have? You are free to ask me any questions. Yes, Abdul?
It's clear so far, clear, sir.
So far clear. Okay. Now, what I'm moving to the last topic of the session is basically we'll see into some part of inferential statistics. We did with the descriptive statistics. We did with hypothesis testing. We did with p-test, t-test, and all the parametric tests, right? So we'll just venture out and we'll just have a final overview of how these particular tests playing a very, very important role. So the topic on inferential. What are the things we completed in our descriptive statistics, Abdul? What are the parts that we completed as a part of our descriptive statistics? You did with the descriptive statistics, right? So what are the things we did in the descriptive statistics? Any idea? What are the things we have done in the descriptive statistics? Let me have a. So we did with the probability today, right? We did with the probability. We did with the sample space. We did with the event space. We did with the conditional probability. Then we've seen the cumulative density function. And then the distribution, very important, Bernoulli's distribution, binomial and normal distribution, Poisson's distribution, and exponential distributions, right? So Bernoulli's distribution has only two possible outcome, 1 or 0. So that is what is your Bernoulli's distribution. Then this is an experimental outcome of your Bernoulli's distribution that we generate particular case with identically true or false. Then we have normal distribution where we have a bell-shaped curve, and here the total area under curve is 1, where the mean and the standard deviation. So here your mean, that is which you use, is basically 0 standard deviation 1, and then this is a normal distribution and a standard deviation that we have seen. This is a skewed distribution that we have seen, the negatively skewed and positively skewed. A model how it works for the distributed data, that is a skewed distribution. Then the z-score that defines the number of standard deviation expected value that we can see. So the positive z-score, the observed value is the z-standard, that is the deviation to the right of the mean. Negative z-score, that is the value to the left of the mean. So this is the formula how we calculate the z-score. Then this is a normal distribution. What is a normal distribution, Abdul? Why do we use normal distribution? Any idea why do we use normal distribution? Yes, Abdul? Why do we use normal distribution? To check whether our data is normally distributed or not. So to check the normal data is normally distributed or not, we use the normal distribution, and also we use the standard normal distributions, right? So we use the normal and the standard normal distribution. Then we did with the conditional probability for a particular event being true when the another event is false. So that we calculate the conditional probability. That is the mutually two event cannot take place together, or the one of the event from the list must occur for sure when the experiment is performed. That we have done, which is the case of your conditional probability. Then we did with the Bayes theorem, where we did the posterior probability, prior probability, likelihood of a probability, and the evidence, and descriptive and inferential statistics. So as a part of descriptive statistics, we did mean, median, mode, standard deviation, variance, quantile, maxima, minimum, box plot. Inferential statistics, we did inferences where we did hypothesis testing and the confidence interval level, that we can check whether your null hypothesis or your alternate hypothesis is true or false. That is a part of your inferential statistics that you inference. In the descriptive statistics, we taken our we did like this. We described the data set using pandas, where we got the mean, standard deviation, mean, quantile one, Q1, Q2, Q3, pandas, the standard deviation and the other parameter as a part of your. Then we did with the box plot, where we have seen the Q1, Q3, Q3 minus Q1. We see the outliers, extremes in a box plot, right? So normal distribution, positively skewed distribution, negatively skewed distribution, all this as a part of a box plot. Outlier detection, we have detected the outlier maximum and the minimum. That is how we detect the box plot, right? So this is what we have done with the box plot. And then what we have done, we did with the covariance, where we signifies the relationship between two variable, whether x and y that varies together, or it can range between minus infinity to plus infinity. So we see the upper and the lower limit for the covariance. That depends on the variance of the two variable which is involved. Then we have seen correlation. That is the measure of relationship between x and y, highly correlated, less correlated, when we have the correlation coefficient as +1, 0.5, -1, -0.9, and so on. So we see a correlation, which is a bivariate analysis, and various plots, xy scatter plot for correlation, and we can use covariance divided by sigma x into sigma y, that is standard deviation, give us a correlation coefficient R. We see Spearman correlation, and we have seen the Pearson's correlation. Then this is the difference between the correlation and covariance that we have done. So the direction of the relationship vary between minus infinity to plus infinity, where it varies between -1 and +1. And the strength and the direction of the linear relationship, it is affected by the scale. It's a autocovariance and autocorrelation. It's mainly used in descriptive statistics, modeling, and time series analysis, that is covariance. Then we have done linear regression, where we use this particular interpretation, y is equal to mx plus c, where we find the difference between the actual value and the observed value, and we find the best value which can minimize the error. That is a part of your linear regression that we have done, and how you calculate the residual analysis in case of linear regression that we have done. Then the models and the metrics for the linear regression that we have done are R square. sum of square, total sum of square, total sum of square error, mean absolute error, and the root mean square error that we have seen mathematically, as well as we did it in Python as a part of your project work with different data set importing CSV file. This is how we calculate R square, where the value of R square lies between 0 to 1. So if it is near to 1, that shows that the R square is very, very significant, right? And then we calculate the mean square root error, that is we call at RMSE. And this is the formula that we calculate the root mean square error, that is the difference between the observed value and the expected value. And this is the interpretation that we generate. So this is the MAE, that is takes the sum of the absolute value of the error, that is the mean absolute error or mean root mean square error, right? And then we predicted the R square value, the root mean square value, the difference between the observed value and the expected value, and what is the output variability, that is we can find out. So hypothesis testing also we did as a part of your regression, where we have taken the null hypothesis and the alternate hypothesis, and we have checked whether your null hypothesis or alternate hypothesis is accepted or rejected. That depends on what? That depends on the value p test or t test that you are using. So hypothesis testing, very important part of your inferential statistics. Here there are three different types of hypothesis testing that we do: one tail and two tail. So one tail is a critical area of distribution, which is either greater than, less than, or certain value can't be both. So that is called as one tail test. And the two tail means the critical area. The critical area of the distribution lies on the either side. The critical area means the region of acceptance and the region of rejection. So one sided is one tail, two-sided is two tail. So critical areas of the distribution is on the either side when your mu1 is greater than mu2, when the population mean is greater than the sample mean, population mean is less than the sample mean, population mean is not equal to the sample mean. So these are the cases of right tail, left tail, and two tail, where is basically the one that we use with important about here is, this is an example whether your null hypothesis will be accepted or rejected. Suppose you rent an apartment or you won't rent an apartment. Your budget is $15,000 per month. So if your budget is $15,000 per month, then you'll go ahead and you rent an apartment. That is your null. Alternatively, you won't rent an apartment if it exceeds your budget. So since your budget is 15,000, you must reject all the apartment whose prices are above $15,000. Hypothesis testing. So here all can come ahead and you can find your critical region based on the budget that you have for your hypothesis testing. So hypothesis testing also playing a very, very important role as a part of your regression or as a part of your inferential statistics. So we have type 1 error and type 2 error. We reject the null hypothesis when the null hypothesis is actually true. Type 1 error, that is alpha. And what is beta? Not rejecting the null alternate hypothesis when the null hypothesis when the alternate is true. That is false positive and a false positive and a false negative. So false negative positive is rejecting a null hypothesis when the null hypothesis is true. A false negative is rejecting alternate hypothesis when the null hypothesis and the alternate hypothesis is true. So that is when you reject a null when the null is true, when you accept a null when the alternate hypothesis is true. That is the types of error. That is a type 1 error and type 2 error. And what is alpha? Alpha is the level of significance. So it is a probability of making a type 1 error as per the standard for 95% level of confidence. 95% level of confidence is your alpha. That is your 0.015. That is 1 minus, you give the 95%. You'll get 5%, that is 0.05. So that is how we check alpha when we go for p-test and t-test in case of your inferential statistics. So type 1 error, type 2 error. False positive, a false negative. Alpha, that is the level of significance. And then we use p-test, that is the p-value, whether it lies within the critical region or whether it lies outside the critical region. If it is lies within the critical region and if it is less than 0.05, your alternate hypothesis will be accepted. If it is greater than 0.05, your null hypothesis will be accepted and alternate hypothesis will be rejected. So that is called as the p-test that we use for hypothesis testing, where we take alpha as 95% or 0.05. Type of test for inferential statistics: ANOVA, one-way, two-way, chi-square test, that is goodness of fit, t-test within a two different group, paired sample t-test, independent sample t-test, and f-test, that is comparing the variance, right? So this is all about your hypothesis testing, where we check the null hypothesis or alternate hypothesis is accepted or rejected. Any doubt, Abdul? Whatever we have done, a quick recap or a brush up on what we have done till now.
Yes, sir. It's okay. Clear so far.
It's okay, it's clear. So let me summarize. It was a marathon session, last 8 classes, and we have completed a lot of things. We did a lot of numericals on basic statistics, descriptive statistics,
Yes.
inferential statistics. We did regression, we
It was
did
a super
ANOVA in
marathon
regression, we did ANOVA in regression, we did normal distributions, skewness, kurtosis. Then we did parametric, non-parametric test, p-test, t-test. Then we did with the numericals on mean, median, mode, standard deviation, variance. We did Q1, Q2, Q3, quantile 1, quantile 2, quantile 3. We did maximum, minimum. We worked with different data sets in NumPy, Pandas, and Matplot. We did 3 to 4 projects, including the libraries NumPy, Pandas, sklearn, and Matplot, PyPlot. We did the implementation of both the descriptive and inferential statistics with Python, with NumPy, Pandas, sklearn libraries, and Matplot, PyPlot.
Yes.
We did with regression and correlation. We did with the correlation and their types, such as your Pearson's correlation and Spearman correlation. Then we did with the
Yes.
probability. We did with the conditional probability, Bayes theorem, sensitivity and specificity. And last, we did with all the revision and exercises, whatever we did since the starting. So with this, we complete our stipulated classes or the time schedule for all the 8 classes. And I also helped you in number of ways to help you to solve your assignments and discuss numerical projects and assignments, similar type of projects and assignments I have solved. So I hope I have been able to complete your entire curriculum for mathematics for data science. Okay, so this is a concluding session. I wish all of you all the best for your project and for your examination ahead. So that's all for today's session. If you have any doubts, any queries,
Thank you.
you are free to ask.
I just
Okay.
haven't.
Yes, Abdul, tell me.
Yes. Yes. Thank you so much. Also, thank you so much, sir, for of the session time you have helped out. I have emailed you, and I wish I can email you again in future also if I have any queries. If you don't mind, I just need to take your permission.
You are or more queries, you can mail me, you can get me, and I am very particular. I reply to your email. So even after 10
Yes.
days or after a week, if you find that you're getting stuck somewhere, you're most welcome to mail me, and I'm there at the other end, at the receiving end, to clarify your doubts. So I have mailed
Yeah.
all the stuff, all the projects, all the assignments, whatever we discussed in the class. So
Yes, your voice is
I'll
cutting.
get ahead.
As you mentioned earlier, it was a marathon, but not. I would say honestly, it was a super marathon. I am. I can. Your voice is not audible, sir. Sorry, sir. You're not audible. Sir, if you can hear my voice, please do email this PDF file for our reference further. So if we have any doubt, we can revert back to you.
Yes, yes, I will mail the PDF and I'll mail the entire stuff, whatever we have discussed till now, till date. Okay.
Thank you so much, sir. It was nice, but honestly, it was a super marathon classes. Lots of things we have to still practice, but thank you so much. The way you have taught us, it was really enjoyable, and thank you so much again for being us as a mentor and teacher.
Thank you. Wonderful feedback. So see you all. In any case, any doubt, you're free to contact me via my email and I'll definitely go ahead and reply to your mail, right?
Sure, I will bother you, sir. I hope you will not mind it.
No, not at all. It's my pleasure to reply you all. Okay. Bye bye.
Thank you so much, sir. Thank you so much.
I'm hereby ending the meeting. Bye bye.
Sure. Thank you, sir. Bye bye.